Space is big, and it's getting bigger. But where does all that new space actually come from? And is it popping into existence around you right now? Is that why the remote control is always further away than I thought? Nearly 100 years ago, a collection of observations and theoretical ideas came together to reveal that the universe is expanding on the larger scales. The distant galaxies are all racing away from us, and interpreted through the lens of Einstein's general theory of relativity, this only makes sense if all distances everywhere are increasing evenly. This revelation led to the discovery of the beginning of the universe at the Big Bang, and it lets us predict its future. It'll probably expand forever, FYI. We know the effect of cosmic expansion on the most enormous scales, but what about the here and the now? If space is expanding everywhere, is it expanding inside the solar system? Inside you? And what does it even mean for space to be expanding? Does that stretching stretch space thin? Will it eventually snap like overdrawn taffy? Or does new space get created on the fly? In which case, where does it come from? Objects in space tend to move around due to nearby gravitational influences. Planets orbit stars, stars orbit in the mutual gravity of their galaxies. Galaxies whirl and collide in local groups and clusters. But if you expand your view to large enough scales, that local motion or peculiar velocity is small compared to the fact that distant points are moving apart, receding, and the further distant, the faster the recession. We call this the Hubble flow, after Edwin Hubble, the guy who first measured the rate of this expansion. The Hubble flow could be interpreted as everything moving through space, but there's a cleaner picture. Soon after Einstein finished general relativity, 4 scientists independently solved its equations for the entire universe, giving us the Friedmann-Lemaitre-Robertson-Walker, or FLRW, metric. You can think of a metric as the coordinate system of a patch of space-time. Similar to how longitude and latitude are the coordinate system of the 2D surface of the Earth, a metric in general relativity is the coordinate system of a chunk of space-time with 3 spatial and 1 temporal dimensions. And just as latitude and longitude describe the spherical geometry on the surface of the Earth, the FLRW metric gives the geometry or shape of the universe. The spatial part of that geometry would be the 3D analogue of our surface of a sphere, which would be a space that loops back on itself in all directions. Or it could be an infinite plane, either flat or hyperbolic. These shapes can be thought of as 2D slices out of 3D spaces. But those 3D spaces are just slices out of 4D space-times, representing single instants in time. If you use general relativity to track how the FLRW metric changes over time, you find that it has to change, either growing or shrinking in size everywhere evenly. The FLRW metric makes some pretty big assumptions. That matter in the universe is perfectly evenly spread out, homogeneous. And it looks the same in all directions, isotropic. These seem to be a good representation of the universe on the larger scales, but keep this assumption in mind, it'll be important to notice when it's wrong. Okay, just for laughs, let's look at the math. This is the FLRW metric. It's basically Pythagoras for 4D spacetime. The squared distance, in this case proper distance, between 2 points is the sum of the squares of the x, y, and z, but here adding the dimension of time. And this thing is the scale factor. It represents the overall size of the universe, and it's the thing that has to change. In our universe, it's getting bigger. When we say the universe or space is expanding, we mean that the scale factor is getting bigger. But what does that mean beyond the math? What is physically happening? There's a classic classroom representation of the expanding universe that's actually pretty useful here. Glue galaxies to a balloon and inflate. The galaxies recede from each other with apparent speeds that are proportional to distance. But the balloon analogy isn't even really an analogy. At any one instant, it's a fair representation of a 2D slice out of a closed universe, and its growth represents the increase in the scale factor over time. The FLRW metric, the coordinate grid of this slice, could be represented in spherical polar coordinates. In that case, it looks a lot like latitude and longitude. Those lines are smooth because of our founding assumptions of homogeneity and isotropy. But if we zoom in, we can see that the shape of the grid lines change. They pull towards massive objects like galaxies. In fact, the shape of spacetime around massive objects is not the FLRW metric because matter isn't spread out evenly. For example, near a massive compact object, the correct description of the spacetime is the Schwarzschild metric. The space in the Schwarzschild metric by itself does not expand. In fact, space is pulled inwards, pinched, and is completely static over time. But what about if it's embedded in a larger FLW spacetime? Does the underlying expanding sphere fight against the inward pull of gravity? Is the space inside, say, a galaxy growing, but overcome by the gravitational attraction between the stars? The answer is no. Space within any gravitationally bound system is unaffected by the surrounding expansion. In the balloon analogy, it's tempting to think of the galaxy as being held together despite the expanding material that it's attached to, but that's not what's happening. The gravitational field isn't something that lies on top of the fabric of spacetime. The gravitational field is the fabric of spacetime. If the gravitational field of the galaxy is this static, inwardly pinched grid of the Schwarzschild metric, then that's it. That's the spacetime in that area. There isn't another underlying expanding grid that field has to fight against. In fact, the spacetime inside the Milky Way doesn't even know that the universe is expanding. The other way the balloon analogy fails is that the fabric of spacetime doesn't get stretched in the way the rubber gets stretched. It doesn't thin out and it doesn't build up tension in a way that can pull against these embedded static fields. It's as though the balloon adds more rubber as it inflates, always maintaining the same level of stretch. Let's try something else. Lose another dimension of space, so the universe becomes an expanding ring instead of a sphere, with grid points instead of grid lines. But then we can add the dimension of time into our picture so that the expanding ring traces a sort of cone and the points trace lines. This is nice because you can show the changing rate of expansion. Perhaps a period of rapid accelerating growth during inflation, then the expansion slows under the influence of gravity, then dark energy takes over and expansion accelerates again. The expansion of space is seen in the divergent of our FLRW coordinate grid lines. Now the distance between those lines represents the growing scale factor. Let's zoom in again. What does an individual galaxy look like? If the galaxy causes grid lines to be pulled together on a sphere, then on a ring it causes points to be pulled together, and they maintain that separation as the ring expands. So on our expanding cone, we see distant grid lines diverging, but nearby lines in a gravitational field will remain parallel. So there is no constant tug of war between the expanding universe and the gravitationally bound systems it contains. That tug of war did happen, but it happened a long time ago. In certain regions, expansion won, and threw apart objects and the spacetime grids they trace. But in sufficiently dense regions, gravity won, and there the only evidence of the greater expansion comes from the receding view of distant galaxies. I told you that space doesn't get stretched out like rubber. In a sense, new space gets created as it expands. But what does that actually mean? Well, this is a tough one. In fact, an impossible one, because we don't have an accepted theory for what the fabric of space is actually made out of, if it's made out of anything. That's the province of a long-sought theory of quantum gravity, but let's see what we can say with what we know. In general relativity, space can be infinitely divided. That means we can start with a universe that's small and grid it up and watch it expand. Those grid lines diverge, but we can choose to regrid it at any point. What was once a millimeter might become a meter, and a meter becomes a kilometer, but we can just redefine everything and start over. We'll never run out of subdivisions. Similarly, we can take the universe of the present and define a grid of space or a grid of points on our 1D ring universe, and then rewind the universe, and every single one of those points traces a path back to the Big Bang. We can make the starting grid as fine as we like and get the same result. Every point in the modern universe can be traced back to a point at the Big Bang. This is related to the idea of geodesic completeness, which we've talked about before. All spacetime paths can be traced to the infinite future or past until they hit a singularity, like the Big Bang or a black hole. As the universe expands, we don't have new patches of space appearing between the old patches to fill out the universe. Geodesics don't just pop out of nowhere. This all works if space is infinitely divisible. But we know that on the smaller scales, general relativity comes into conflict with quantum mechanics. There is a smallest measurable length called the Planck length. When space expands, what happens to this smallest length? Does it expand too? Well, the Planck length stays the same. It's just defined as a combination of the gravitational constant, the Planck constant, and the speed of light. So if those aren't changing and there's no evidence that they do change, then the Planck length remains the same. But as the universe expands, it adds more and more of these Planck lengths, which must expand out of the old Planck lengths. That implies an infinitely divisible space emerging from each Planck length. This apparent conundrum is related to something called the trans-Planckian problem, which is to do with how Hawking radiation seems to emerge from sub-Planck wavelength radiation at the event horizon of a black hole. Its solution takes us to the realm of the holographic principle, and so we can't go there today. But long story short, even with a quantized fabric of space, it's still possible to expand it or condense it infinitely without changing its fundamental nature. Empty space can be rescaled infinitely. And that's even true if empty space contains something, like dark energy. Empty space does have a very weak energy density, even in the absence of particles. As space expands, that density doesn't change. Remember, the balloon skin doesn't thin out. The result of this is that the total dark energy content of the universe depends on the amount of space in the universe, which means dark energy increases as the universe expands. But again, this will never have any effect inside bound gravitational systems. Its effect only manifests when there's an enormous amount of empty space compared to the amount of matter. But the ratio of empty space to matter inside galaxies does not change. Now, if the level of dark energy per unit volume were to increase, that would be a different matter, and we talked about the resulting cataclysm in our episode on the Big Rip. So, there's your answer. The infinite rescalability of space means the universe can and probably will expand forever with no effect on this little bubble of relatively static space that we call the Milky Way. Well, except for permanently isolating our bubble from all of the other bubbles. Let's just be grateful that we came into being soon enough to catch a glimpse of those receding galaxies. They will spend most of cosmic time far beyond the horizon, in which case we never would have known that we even live in an infinitely expanding space-time. Today, we're looking at your comments from the last two episodes. There was the one on John Archibald Wheeler's participatory universe, and the episode on the Higgs mechanism and the mass of the W boson. Let's do the latter first. 747 Tufar asks, how the heck do you weigh a subatomic particle? Good question. Riley Schroeder quips carefully and hypothetically, which is correct in the sense that you don't measure it directly, like not with a subatomic set of scales. Fernando, who was one of the three of us who pulled our hair out writing this episode, gave the correct answer. When a charged particle is created in a particle collider, it travels through the powerful magnetic fields of the detector. The amount by which the path is deflected by that field depends on its mass. In the case of the W boson, the particle actually decays too quickly to measure its mass directly, but you can measure the masses and kinetic energies of its decay products and determine the mass of the W. Some of you reasonably point out that it is potentially misleading to use terms like observation or conscious awareness as the causal event that collapses the wave function, or in this case manifests the universe, rather than saying that, for example, interaction is doing the work. It's very true that the choice of phrasing has led to all sorts of misunderstanding and quantum charlatanry, but I think the reason people like Wheeler and Niels Bohr used these terms is because their conscious observation of the system is literally the only event that they can be sure actually happened. They were being philosophically honest by adhering to pure, stripped-down logical inference from the style of Descartes. They felt it dishonest to start their train of reasoning with statements about external factors that they couldn't directly observe. Unfortunately, practitioners of quantum woo are not so careful and definitely not so honest. Lyman Brown Whitehill reminds us that the participatory universe isn't the first of Wheeler's wacky-sounding ideas. The other famous one is the one-electron universe, in which all electrons are actually the same electron bouncing back and forth in time. Wacky as they are, they tend to have legs, these ideas. In his Nobel Prize acceptance speech, Richard Feynman admitted to stealing the time-travelling electron thing from his advisor, Wheeler, and using it to help develop quantum electrodynamics. So what can we build using the ideas of the participatory universe? Meat Source Z invites us to address the elephant in the room. If the participatory universe interpretation is true, then what are the entities that initiated the first interaction that brought everything into being? Well, actually, I think this is exactly the issue that Wheeler was trying to find a way around, the issue of infinite regress. How do you identify a founding cause by tracing the causal chain backwards? In Wheeler's mind, the only universe that can exist is the one that causes itself. That's what he meant by a self-excited circuit. It put me in mind of the way the electron in the admittedly outdated Bohr model of the atom, in a sense, creates itself by constructive interference. Only electrons whose wave functions, peaks and valleys line up on each orbit can exist. Maybe the universal wave function is just that wave function in the space of infinite possible wave functions that constructively interferes to reinforce its own existence. Speaking of which, several of you noticed that this video was posted on 420. I swear that was a coincidence. Like, whoa dude.